Welcome everyone to the 12th lecture in the lecture series on circuit and system. I am Nikhil Kumar Nigam from AAA Department, Delhi Technical Campus. We will start by having a recap of what we have discussed so far in the last lecture, and then we will start with today's objective. So in the last two lectures we discussed static and dynamic systems, and on performing some numericals we draw some conclusions that a system whose output is dependent on time scaled input, these are dynamic systems. That is, if we have a system whose output is dependent on the input and the input have a time scaling, then the system will be dynamic. Similarly, if input have time shifting, the system will again be dynamic. Or if the output is dependent on the integration of the input, the system will be dynamic. Or if the output of the system is dependent on the differentiation of the input, then the system will be dynamic. This we draw in the last lecture. And in the last lecture we discussed about the causal and non-causal systems. Causal systems are one which depends only on the past and present values, and if the system is dependent on future values as well, then the system will be non-causal system. Actually, in practical sense, we can have only the causal systems. We cannot have any non-causal system. So to prove that the given system is a causal one, it is very necessary when we are synthesizing a certain network or a system, because we can synthesize only the practical systems. We cannot synthesize any impractical systems. So non-causal systems were impractical. So on the basis of numericals we draw some conclusion that whenever there is a time scaling in the input, the system will be non-causal. And similarly, if there is a time delay, that is, if the input of the signal is time shifted with a time delay, then the system will be non-causal. Today and in the last we discussed the time variant and time invariant system. So in this lecture we will discuss the different type of systems. We will discuss the time variant and invariant systems. So in this lecture we will discuss linear and non-linear system, stable and unstable system, and we will also discuss some numerical problems on time variant and invariant systems. Let us have a recap on time variant and invariant system. A system is said to be time invariant if any time shift in the input brings about the same amount of time shift in the output. Say we have a system xt, and it is inputted into a system, and we have got yt as the output. Now if instead of xt we input a signal called x of t minus t naught, that is a delayed signal, into the same system, then for being this system to be time invariant, it must produce an output which is also time delayed by the same factor by which the input has been delayed. So to check this, what we will do, we will first find out y of t minus t naught, that is whatever the output we are provided with. Say we are provided with yt. From this yt we will calculate y of t minus t naught, and then in the same system instead of xt we will then substitute x of t minus t naught. And if these two, that is the response of the system after the excitation of x t minus t naught, is coming out to be equal to y of t minus t naught, then we will say the system is time variant. It will become more clear with the examples. Say this, we have y of t is equal to 2 times of xt, and we have to check whether the system is time variant and invariant. let us see this. Say if I bring delay in the output, delay in output. So if we have yt, then delay in output will be reflected as y of t minus k. Say a delay has been the system has delayed the input by the factor k. So it means this, wherever we have t, we will wherever we have this t, we will delay it with the factor k. Now the system is, this yt is actually 2 of xt. So it means this, if it is the time factor and it is being delayed, so we have time factor t here. So in the output, on delaying the output, we have 2 of x of t minus k. That is where we had the time factor t here, so we bring the delay in t here by subtracting k factor. Similarly, let us check for the delay in input. Delay in input, that is, instead of xt, we will input x of t minus t naught. So this expression is saying that if we are inputting xt in the system, then the output is 2 times of xt, and if instead of xt we are inputting x of t minus t naught, then in the output we will get 2 times of x of t minus k. Oh sorry, t minus this should be t naught or k. Let me consider this k. So when I excite the system with a delayed input, the response is 2 times of x of t minus k, and from this equation and this are same, and when the delay in input is reflected as the delay in output, then we will say the system is time invariant system. So this is time invariant system. Time invariant system. Let us discuss this example now. We have yt equal to x of 2t. Now let us bring the delay in output. Now this will be, instead of yt, we will bring a delay in output, that is we will get y of t minus k. So if yt is x of 2t, then whatever the time we had here, we subtracted minus k here to bring the delay. Similarly, if I want to bring the delay of factor k here, then I will subtract this k from this factor 2t. This means on delay this will appear as x of 2t minus k. So this is the output when we bring delay in the output. Let us now see the delay in input. That means we will now excite the system with t minus k. That is, instead of t, I will excite the system with t minus k. Now when I excite the system with t minus k, the output should be, I am replacing t with t minus k, so the output is x of 2t. That is, I need to replace t with t minus k. So in the output I will get x of 2t minus 2k. Now if I compare these equation 1 and 2, I will see the output over here is x of 2t minus k, and over here it is x of 2t minus 2k. Obviously these two are different. If these two are different, we will comment that the system is time variant system. Time variant system. Let us discuss more. Now this time I have yt. Let us go back and draw some conclusion first. In this example, we saw that over here we have scaling of the function, scaling of the input signal, but in here we have scaling of the time. So whenever there is a scaling in time, the system will be time variant, and whenever there is a scaling of the signal, the system will become time invariant system. So remember this. Let me put it in words. Time scaling will make the system time variant system. Let us move ahead. If you remember, we draw certain conclusion in the last slide that whenever there is a time scaling, the system will be time variant. And as we can see in this example, we had scaling in the signal as well as scaling in the time. So this factor is representing the scaling in time. So this will make the system to be time variant system. Let us check this. Say we have let us calculate the delay in output first. Delay in output, the delay in output would be by the factor k. So the delay in output will be t minus k. What are we doing here? Whatever the time we have with y, we are delaying it by the factor k. So whatever the time we had in the equation here, we had time as sin t. So I will bring a delay and it will become 2 times of x of sin t minus k. This is the previous time, and we have brought a delay of minus k in this equation, and this will appear something like this. Say this is our first equation. Now let us bring the delay in input. Delay in input, that is, if we excite the signal instead of xt by x of t minus k, the output will be, say the output is y dash t, say the output is y dash t, and it will be equal to, we will replace t with t minus k in the equation. So we will get 2 times of x of sine t minus k, like this. Say this is our second equation, and if I look here, I can clearly see the equation 1 and 2 are different, because over here we have sine t minus k, over here we have sine of t minus k, and these two equations are very different. Hence I will comment that the system is time variant system. System is time variant. I hope you are getting this. What we are doing here, while bringing the delay in the output, we are just looking what is the time here. We have inside the bracket, it is giving us the time, so we are bringing the delay in it by subtracting it with k. And while finding out the delay in input, we are substituting t with, wherever we had t in the equation, we are substituting t with t minus k, and then these two equations are different, so we are commenting that the system is time variant system. Let us check this example. This example is again very similar to this one. We had scaling here with the function of sine, and over here we again had a scaling of time by the function of exponent. So I can directly say that system is time variant, but in the university exams we have to solve it. So let us solve it. Let us bring a delay in output. So delay in output will be ty of t minus k, and wherever I am getting the time instant, I'll bring the delay. Here the time is t and over here the time is et. So it will be equal to x of e raised to power t minus k. So I'll delay this time with this. But while calculating the delay in input, we had y of, say, y dash t as the output. When I bring delay in input, that is, I will substitute x of t minus k instead of xt. Now I will excite the system with x of t minus k. So y dash t will be equal to, I will replace t with t minus k. So in this equation, this will become x of e raised to power t minus k. And obviously equation number 1 and 2 are different, because it is e raised to power t minus k, where this is e raised to power e to the exponent of t minus k. So these two equations are different. So I will say, or I will comment, the system is time variant system. Time variant. So whenever there is a scaling in the time, we will comment that the system is time variant. So in the last four numericals, we concluded that whenever there is a time scaling, it will make the system to be time variant system. Let us check these two numericals also. What is here? We have yt, which is equal to sine t times of xt. That is, we have this signal xt here, we have this yt here. Now if what this equation is saying, let me illustrate. Say I excite the system with xt. If I excite the system with xt, whose dynamic equation is given by this, then in the output I will get sine t times xt. So that means what this system is doing, it is taking a signal in the input and it is multiplying the signal with sine t, and it will feed it to the output. So this is the output. So if I calculate the delay in output, so whatever the time we have here in the equation, I will substitute this time, delay this time with t minus k. So the delayed in output y of t minus k, this will be equal to sine of t minus k, because we had time here t minus k, and we had input signal x of t minus k. Now let us bring a delay in input. If I am bringing a delay in input, it means this: instead of xt, now I am feeding x of t minus k. When I feed x of t minus k here, then in the output I will get the this system. What this system will do, it will multiply the input signal with sine t only. That is, in the output, let me say the output would be sine t times x of t minus k. Say this is my first equation, this is my second equation. Now we can see that these two equations are different by this factor because of the presence of this factor here. So if these two are different, then we will say the system is time variant. The system is time variant system. Let us solve this numerical now. We have yt equal to e raised to power t xt. Let us solve it in the same way. That is, I will input the signal xt into the system, and in the output I will get e raised to power t into x of t. Let us briefly notice what is happening in the system. Whatever is the input signal, whatever is inputted into the system will multiply the input signal with e raised to power t. So while bringing the delay in output, I will shift the time with t minus k. So that is, the delay in output would be, say it is y of t minus k. This will be equal to e raised to power t minus k times x of t minus k. That is, wherever we find t, we delayed it by the factor k. Now let us calculate delay in input. So instead of substituting or feeding xt, I will feed x of t minus k here. Now if I feed x of t minus k here, so what the system will do, it will not change this input signal, it will just multiply it with et. So the delayed output is, let me say it is e raised to power t times x of t minus k. Say this is my first equation, say this is my second equation, and on comparing these two equations I can see these two things are different, hence the system is time variant system. So from this we can generalize the result, that if the input is scaled, here the input signal is scaled by a time varying system or time varying function. Here this xt is being scaled by a time varying signal. Similarly over here this xt is scaled by this time varying system or signal, then the system will be time variant. So I can comment that whenever there is a scaling of input signal by a time function, the system will become time variant system. So I guess we have discussed enough numerical problems on time variant and time invariant system. Let us proceed further. We will now discuss linear and non-linear system. You must be hearing about or discussing about the linear and non-linear systems since the first year. As defining any system to be linear, it makes the calculations or analysis a bit easier. So why we try to prove that the given system is linear, because the non-linear calculations are very tough. So why we approximate even the non-linear system to be to its closely linear approximation. So we will now define we will give a clear definition of linear system. A linear system is one which follows the law of additivity and law of homogeneity. Whenever a system follows the law of additivity and homogeneity, we will say the system is linear, and if any of the two is not followed by a system, then the system will be non-linear. Let us discuss the law of additivity first. What this law of additivity says. Say we have a system which is excited by xt. We have this system which is excited by this xt, and it is producing the output yt. Now instead of xt, let me say the same system is excited by x1t. It is a different signal, completely different signal from this, and it is excited, it is being fed into the same system. Then in the output I will get y1 of t. And if I consider another signal x2 of t, and if I excite the same system with this signal, and let me say the output is y2 of t, and and in the end, if I excite the system, same system, with the addition of these two signals, that is x1t plus x2t, then let me say the resultant is y3. Now if this resultant y3 of t comes out to be equal to the addition of y1t and y2t, then we say the system is following the law of additivity. What is y1t and y2t? We have already discussed this as the law of superposition. Where y1t is the effect of x1t, y2t is the effect of x2t, and when the system is excited by both the inputs, then the resultant should be the sum of the individual results. So the resultant should be the sum of individual results. If this equation is followed, then we say the system is following the law of additivity. Let us discuss the law of homogeneity now. The law of homogeneity says if we have this system, which is excited by this xt, and it is producing an output of yt. Now if we input a scaled version of this input xt, then in the output we should get k times of y of t. That is, if we scale the input signal by a certain factor, then the output must be scaled by the same factor. If the scaling in input is reflected in the scaling in output, then we say the system is homogeneous, or it is following the law of homogeneity. If these two are not equal, that is when we are exciting the system with kx of t and we are getting say k dash of yt, that is these two are not that is k dash and k is not same, then we will say the system is not following the law of homogeneity. So whenever a system follows the law of additivity as well as the law of homogeneity, then we say the system to be linear. Okay, let us now discuss some numerical problems on the basis of this. We are provided with these two numericals. Let us discuss this numerical first. We will try to prove whether this is we will try to check whether this particular numerical is a linear system or a non-linear system. So first we will check the law of additivity. In the law of additivity, we will first excite the system with, when system is excited by x1 of t, then I will get y1 of t. And what the system is saying, that if we are exciting the system with xt, I am getting x of t plus 1 in the output. So in the output I will get x1 of t plus 1. Similarly, if I am exciting the system with x2t, then in the output I will get, say I get y2t, which will be equal to x2 of t plus 1. Now what will be the output when I excite the system with x1t plus x2t? That is, when I excite the system with this, what will happen? Whatever is inputted, if I am inputting the signal xt, then it is getting converted into xt plus 1. So if I input this, then in the output I will get, say I get output as y3, which will be equal to x1 of t plus 1 plus x2 of t plus 1. Now we can clearly see that y3 of t is equal to y1 of t plus y2 of t. The y3 is equal to the addition of y1t and y2t. Hence we will say it is following the law of additivity. That is, it is following the law of additivity. Now we will check the law of homogeneity, law of homogeneity. In the law of homogeneity, I will excite the system with k xt. Now if I excite the system with k xt, then instead of xt, I will now excite the system with kxt, and in the output I will get k times of x of t plus 1, because it is the system is not changing the scaling factor of the input signal. So whatever the scaling factor here, it will be reflected in the output. So we will say, as the scaling factor has not changed even after shifting, then we will say the system is following the law of homogeneity as well. Now I will comment that as the system is following the law of additivity as well as law of homogeneity, then the system is linear system. We will now check whether this given system is linear or non-linear. Let us check the law of additivity for this numerical. Law of additivity. So in the law of additivity, I will excite the system with x1t. Let us understand this system first. That is, if I excite the system with xt, then in the output I am getting x of t square. So if I excite the system with x1t, I will get, say, y1t as the output, and this will be equal to x1 of t square. That is, system is changing the scaling the time only, the time of the input signal. It is not changing anything in that signal. So if it is x1, it will be reflected as x1. But the thing is that it will, this t will be scaled. Now let us check. Let us calculate for x2t. Let me say the output is now y2t, and this is equal to x2 of t square. Now if I excite the system with x1t plus x2t, then say the output is y3t, and it will be equal to whatever is the signal here. The only change in the signal coming is that only the time is changing. So if we are inputting x1t plus x2t, so in the output I will get x1t square plus x2 t square. Now if I check, or if I notice, y3t is equal to y1t plus y2t, that is, this is equal to the summation of these two. So I will say that it is following the law of additivity. So law of additivity is verified. Now I will check the law of homogeneity. Law of homogeneity. In the law of homogeneity, instead of xt, I will now excite the system with k times of xt. That is a scaled input now. As we can see, if its magnitude over here is 1, then it is also 1. That is, the system is not changing the magnitude. So while exciting the system by a scaled input, I will get k x of t square. So I can see the scaling has the same scaling factor has appeared in the output. So I will say the law of homogeneity is also verified, and as the system is following the law of additivity plus law of homogeneity, so the system is linear system. So I can draw certain general conclusion from here. So the general conclusion is, with the time shifting or time scaling in the input signal, there will be no effect on the linearity of the system. Let us discuss another examples. We have yt equal to x of cos t here, Let us check the law of additivity first. Law of additivity. This signal is saying that if I am exciting the system with xt, I will get x of cos t. That is, it will change this time t with cos t. So if I excite the system with x1t, in the output I will get, say, y1t, and this will be equal to x1 of cos t. And similarly, if I excite it with x2 of t, I will get, say, y2t, and this will be equal to x2 of cos t. Now let us excite the system with x1t plus x2t, and say in the output I am getting y3t, and from this what will happen? In the output I will get x1 of cos t, x1 of cos t plus x2 of cos t. Now if I notice that y3 is coming out to be equal to y1 plus y2, that is, y3 of t is coming out to be equal to y1t plus y2t, and as these are equal, that is, I will say it is following the law of additivity. Now let us check the law of homogeneity. In the law of homogeneity, instead of xt, I will excite the system with kxt, and I can clearly notice that there is no effect on the scaling factor, so I will get k times of x cos t. That is, the same scaling factor has been produced in the output as that in the input. So I will say the law of homogeneity is also verified. So as it is verifying the law of additivity as well as law of homogeneity, then the system is a linear system. This is a linear system. We can again generalize this, that there is a scaling, time scaling, and it is not affecting the linear system. Similarly, there is time scaling, so this will also come out to be a linear system, and I am leaving it on to you to solve the numerical as per the given process and have a practice over it. Let us move ahead. Let us check this. We have y of t equal to x of t to the whole raised to the power n, and let us check this whether the system is linear or non-linear. If I check the law of additivity, then this says, the system says that if I excite the system with xt, in the output I will get xt raised to the power n. So if I excite the system with x1t, let me say the output is y1t, and this will be equal to x1t raised to the power n. Same x2t, if it is the signal, then in the output I will get y2t, and this will be equal to x2t raised to the power n. Now if I excite the system with x1t plus x2t, and let me say I am getting y3 as the output, then as per this the output will be x1t plus x2t to the raised power n. Now I can clearly see that y3t is not equal to y1t plus y2t. That is, it will not be equal to, obviously it will not be equal to x1t square or n plus x2t raised to the power n. So as it is not following the law of additivity, I will comment that the system is non-linear system. Non-linear system. So the scaling of the input signal by a certain exponent can make the system to be non-linear. Let us move ahead. We are now on to the final classification of the system. We will classify now system as stable and unstable. We classify system as stable if bounded input produces a bounded output. A bounded input produces a bounded output. What is a bounded input? In the time duration of -infinity to infinity, if the magnitude of the signal is limited, that is, or I would say is finite, then we will say the signal is bounded. So for bounded input, the system must produce a bounded output. If for a bounded input system is not producing a bounded output, in fact it is producing an unbounded output, then the system is unstable. This is called BIBO stability. B-I-B-O stability. Bounded input, bounded output. A bounded input must produce a bounded output. If a system is following this, the system is said to be stable. If a bounded input is not producing a bounded output, then the system is not stable. What are unbounded output, unbounded signals? Let us see. Say we have ut. We know the magnitude of ut is always 1. That means it is an example of a bounded input. Similarly, a DC signal, it will again be an example of a bounded input. Sine omega t, we know it can maximum go to +1 and it can minimum go to -1. That is, during all the intervals from -infinity to infinity, it will have its magnitude between 1 and -1. Hence the signal is bounded signal. So these signals are bounded signals. And if I see RT, I know RT at t equal to infinity, RT is equal to infinity. So this is an example. RT, that is ramp signal, is an example of a unbounded signal. This is unbounded signal. Similarly, if I check e raised to power at, that is for a to be positive, and at t equal to infinity, this will become infinity. So it is also an example of a bounded signal. But if I see ut times e raised to power -at, then this product will be an example of a bounded input, because its magnitude will always be limited between 1 to 0. Let us see whether this is the given systems are stable or unstable. Let me say, if instead of xt, if I am exciting this system with a DC signal of 4 volts, then the yt will be, yt is coming out to be 2 into 4, that is 8 volts. That is, on the excitation with a bounded input, we are getting bounded output. And as the system is verifying the BIBO stability criteria, we will say the system to be stable. Now let us check this example. Now if I multiply the, if I excite the system with DC signal, that is of 2 volts, say, that is x of t is equal to 2 volts, then yt will be equal to 2 times t. And now at t equal to infinity, y of t will be infinity, as a bounded input is not producing bounded output, we will say the system is unstable. Remember this is a very important criteria while selecting or checking whether the given system or design system is stable or unstable. We will use it in the later lectures or in the later units, I would rather say. So that's it for this lecture. Thank you so much for listening to the lecture. You can mail me your queries at n.nigam@delhi-technical-campus.ac.in, or you can WhatsApp me your queries at 9215-949494, or we can discuss your queries in the tutorial classes. So till then, take care, keep learning. Bye bye.